Okay, are we live? Okay, I guess we are live. So my name is Martin. I'm super happy to be with you today. I'm here with Ivan and Tasso to talk about Apollo Android. So Apollo Android is this project on GitHub, open source project talking about GraphQL. And today we are here to talk about how we moved the project and made Apollo Android work on iOS. But before we dive a bit into the detail, I wanted to give a bit more context about GraphQL and what Apollo Android is. So I like to introduce GraphQL as a successor to REST, so it's REST on steroids. The main promise of GraphQL is that the client requests data. The client will request the data it wants, and the server will reply with the exact data. So here I took a GitHub example of a repository with a description and number of stars. And here you can see the response. So this is the request, the GraphQL request from the client. And this will be what will be replied by the server. So you can see, as you can see, it's only what the client asks. So there's no less, no more. So this is the base of GraphQL. GraphQL has a lot of other features which we are not going to talk about today, but two of them are strong typing and introspection, which allows to write great tools like Apollo Android. And Apollo Android, you see it coming, is a tool to generate Kotlin models from GraphQL queries. So at its core, it's a compiler that takes GraphQL requests, the schema that describes all the types in your API, some compiler configuration here, and it will generate Kotlin queries for you that are completely strongly typed. So the nice thing is that the types from your backend appear on your frontend almost magically. This is done using a Cradle plugin. So the Cradle plugin calls the compiler, generate Kotlin models, and these Kotlin models uses what we call the API module. So the API module is really the base core of Apollo. It's where the JSON parsing happens, and also this is where the most basic fundamental data structures are that are going to be used by the rest of Apollo. On top of Apollo core, you have what we call the runtime, which contains a lot of things, a lot of modules. There is stuff for HTTP, there is stuff for caching, RxJava support, coroutines, Android. There's a lot of things there. I'm not going to talk about the details there. The important thing to note is that Apollo core is already 100% Kotlin multiplatform. So you can generate today Kotlin multiplatform models in Kotlin and use them. All the JSON parsing is completely multi-platform, and it works on Android and iOS. The runtime is still experimental, and it's a work in progress. This is why the apple is a bit cut here. So some parts are working, some parts are still under construction, and Ivan will explain at the end of this talk what is currently going on in the Apollo runtime. But enough talking, and I will leave the room to Tasso to explain how we brought Kotlin multiplatform to the Apollo core.
Yeah, so, okay, wait. So this is basically a timeline of our journey to move to Kotlin Multiplatform. The first GitHub issue was open almost like 1 year ago, and we will talk about more details, but a lot of preparation happened. So just February this year, we added the first Kotlin dependency with the little bit of migration, and then first multi-platform plugin was added in March this year, and we finally released the library with amenable support with the API and the code generation, like Martin mentioned, in April. And now we are at Kotliners conference. basically, and then we are right now working on the new runtime where Ivan will be talking more about. So when we started after I was new in the project as well, so this is from August last year. Maybe I had too much time or I was bored. I migrated the complete module to Kotlin, of course, by using the magical convert to Kotlin shortcut in IntelliJ. So, I mean, that was not too hard to do it with the tool. But if it was, of course, not the right way to do it. So this is like the take one we had, but it still allowed us to learn a lot of things. The next approach we tried was by Ivan, and we wanted to separate JVM only parts versus like the common parts into separate modules. Later, we will see that with Kotlin Multiplatform, there is already kind of like an explosion of lots of artifacts because you have for iOS, for Android, etc. separately. But if we separate even more, that is kind of like not that manageable. So we didn't want to go forward with this either, but thankfully Kotlin Multiplatform Gradle plugin is actually really nice and allows you to handle JVM only parts as well. And the other, after lots of discussion in the team, in our Slack channel or in the issues, we kind of ended up with a more iterative approach, which was nicer to do anyways, but it's like an interesting story in terms of our journey. So this was more easier to review, more easier to test changes as well. So it went pretty smoothly after this. And it was also like a really good collaboration between all of us. And like I will go by step by step what we did to turn to multi-platform. So this is gonna only talk about the API module and supporting code generation. So this is like the very, very minimal, let's say, MVP of our project. So first things first, here's the link to the pull request as well. Is actually adding the multi-platform plugin, but not really making the library multi-platform. So the good thing is that Kotlin plugin and the multi-platform plugin shares a lot of things. So you could integrate Kotlin multi-platform plugin by keeping the JVM implementation 100% backward compatible. That is really nice start. So is you just change the plugin, and then here what you do is just have a Kotlin block before you maybe have dependencies block, etc. Instead, you have Kotlin block here. So we started with the JVM. In the initial integration, we don't really have others. So next, you just in the source sets source sets block, you add the common main source set where you have the Kotlin dependency. Potentially, you can have more dependencies here, but they have to be multi-platform. You cannot add JVM dependencies into the common because they cannot be used in iOS. The next one is the JVM part. So you add the Kotlin dependency, any other JVM specific dependencies here. So like most of your dependencies will be here initially because this is keeping it backward compatible with JVM. And the next one is where you can add your testing dependencies like JUnit or whatever. So it is, in short, it is like really the first step without disrupting the code base. You don't really do behavior change. It's 100% backward compatible for existing users. So it's really nice way to do it. Although the Kotlin multi-platform plugin in general is experimental, it is quite fine to do this as a first step. And immediately after this, you can start moving code to the common common code base, common source set. So the next step we followed is resolving the JVM dependencies. So they need to be removed because they cannot really be used in Kotlin native or iOS, right? So there is this really great IntelliJ feature. I use this in general in my company for like really long years in terms like when I do modularization. So this allows you to analyze dependencies. As you can see, I am using it by right-clicking to the Apollo API module uh, to analyze the module dependencies, but you can do for a class or you can do for a folder or package. It's pretty flexible. The next screen, I am choosing the Apollo API module, and then there's this transitive dependencies option as well. If you choose it, it is a much more 100% correct report, but to be honest, you don't need it because you need to have an iterative approach. So you do this without the transitive dependencies, you resolve and do it over and over again until you resolve all the dependencies. So let's look at the report. So production classes, I'm not even showing it because there is not much. That is like dependencies inside your project. So Apollo API is a leaf module. We don't really have another dependency. So this was the first place to start. So that's why it was also easier. One external dependency we have is OKIO, but thankfully it is already multi-platform. So that was easy. The next one is the Java package, basically the one above. So I will go one by one to see dependencies that we have on Java SDK. So basically, this is pretty much common in all projects. So here the IO package is interesting. So the things like you see here, closable, IO exception, flashable. So these are only specific to JVM. So iOS code, Kotlin native does not care. So what you do here, so if you are familiar with Kotlin Multiplatform, you must have watched other talks. There is this expect and actual declaration. So you just declare them again in your project as an expect declaration, and then type alias them to the JVM implementation. And on iOS, you don't really have to do anything. You just create an doesn't care. File is interesting. We had to replace it with file paths because there's no file class in Kotlin native or iOS. The next one is big decimal. So this is an interesting one. I think it was one of the biggest dependencies we had. Big decimal, there's no replacement on Kotlin native. There are some external libraries also, but I will show how we did it ourselves. It was pretty much easy. So you need to do expect class declaration in common main. So here we are not covering 100% of the functions available in big decimal. We are only covering the ones we use, but it's almost all of them anyways. So with that, you can even start using them inside your common main source set and inside your business logic. With Java, what you do is just type alias. And one thing interesting is you see this big decimal extends number. So we didn't do this before in the initial, and JVM tests was just passing because we type alias, and when we type alias, um, it is already extending number. But in iOS code, it was never extending a number, and we have an explicit code checking if a value is an instance of number. So that was failing. We realized that a little bit later, but the tests covered it for us, thankfully. And this is the iOS implementation. You rely on the Apple Platform Foundation NS decimal number, but it is pretty straightforward. Most of the time, you just delegate to the platform implementation, and it is fine for classes like big decimal and the other stuff as well. The other one is the util package. Here you have array list, etc. When you convert code to Kotlin, you might still have imports to Java util map, Java util list. So you just have to replace their import to the Kotlin version. So that is really easy. But if you have reference to the classes, like they are not they are not used that much, but if you have references to classes like stack or concurrent hash map, that gets more tricky. If you have them, like, use this analysis and pick them up as early as possible in the process so that you can handle them more easily later. I will mention one gotcha we had during the process. So this is a bug in IntelliJ, not in the users. It's only available in our project. But once people started to contribute, it's kind of like an annoying to have. You see, it says it requires a throwable type. And an Apollo exception is provided. It's a throwable type already. It compiles just fine. Everything is fine, but it's kind of like a false positive in the IDE. This is just one example. There are more. It's also because we use composite builds in the project, so they don't really work nice together because they are all experimental features. The next step we did is link code in the multi-platform. So we have a Gradle plugin. We had to handle multi-platform parts, especially in the Gradle plugin. So this is not something everybody would need to take care, but this was a next step for us. We are already handling the code generation slightly differently for JVM and Android anyways, so we just had to add another strategy for Kotlin Multiplatform to generate the code in the correct source set. So after doing this, basically we are almost done. It was time to test our implementation. The first thing we did is actually we want to run the test for all platforms. But I will go a little bit quick here because of the time. So there is this dilemma with the Java test, chicken and egg problem. So what we need to do is, first of all, we kept the test in Java while converting. That allows us to make sure that our conversion is backward compatible because there's a Java user already. But once we verified that, a little bit time passes, more usage happens in out there. What we did is convert the tests to Kotlin finally and move them to the common tests. This allowed us to run them on iOS as well, and this actually allowed us to see in issues like extending numbers that I mentioned earlier. In a library, you spend a lot of time, but it is not finished until you have a sample. So we invested a good time on the sample itself as well. So KMP lib sample project uses Apollo, and that's where the network connection, code generation, and kind of like a little bit of a business logic we have is all there. And the iOS part is all just UI. Thanks to Ellen Shapiro from the iOS Apollo iOS team. She implemented in Savytskyi. It's pretty nice. If you are curious, please check it out. Now I will hand it over to Martin to explain the challenges we have with the publication of the library.
Sample app, but now we want to publish it and make it available to the world at large. So first, let's take a look at how we did it previously on the pure JVM project. So in the 1.x branch, you must be pretty familiar with that. We have a jar file with Java code and sources, Javadoc, a POM file which describes the project and its dependencies. It's the Maven format, it's a XML file. And then you have hashes and signatures to verify that you are using the correct artifact. With the introduction of multi-platform, it becomes a bit more complex because you have more than JVM. Now you also have iOS and ARM, iOS for simulator and iOS for device, etc. So the JVM part, it's really what we had before. So this hasn't changed. iOS 664 is for simulator. ARM 64 is for real iPhone devices. You can see here that it's not a jar file anymore, it's a klib, which is the format that Kotlin native uses to distribute native code. And then we have metadata. So this one is a bit specific to multi-platform. It's about keeping all the type information from Kotlin, because if you're on the JVM or if you're on GS or on native, not all platforms support all kind of type systems. So nullability, for an example, is not really a thing on the JVM. And then you have variants and covariants. So all this is type information that Kotlin knows about, but that the other platform do not always know about. And the metadata is there so that tools like the IDE, IntelliJ, or introspection can have access to this extra type information. And then, last but not least, we have this module called Apollo API. So it's the same name as before, but it's almost empty. If you look inside, you will see two files. The POM file, which is the Maven XML file, and the module, which is a new one, which is the Gradle metadata. It's made by Cradle. So if you look inside this Apollo API module file, you will see different variants. And you will actually see one variant for each platform and for each usage, runtime, or API. So really, I like to think of this common module as a kind of a router that will link to the different implementations for each and every platform. If we zoom on the iOS API variant, we can see that the variant iOS API declares attributes. So one attribute says that it's a Kotlin API, another one is the target and the type. And it also declares a link to the actual code. So the actual code, the klib artifact, will be available in the iOS ARM64 module. So all this is called Gradle metadata, and this is a way more flexible way to handle your dependencies compared to the Maven POM model. Gradle says it's variant aware because you can define several variants. Here we had one variant per platform, but you can also have variants, for an example, for GVM 8 and for GVM 11, and maybe even GVM 7 if you are using an old GVM. You can also have, if you're on Android, you have debug and release variants. And this is all very flexible. It uses a producer-consumer model where the producer creates and declares some attributes, and the consumer requires them, and then Gradle is able to match them. So this is all experimental in Gradle 5.3, and this was enabled by default in Gradle 6, which is mandatory if you want to use Apollo 2. This allows to do stuff like not this. So before you were required to declare one dependency for each and every platform, but now you can declare just one dependency. So just one line, and Gradle will look up the individual platform. The nice thing is that it's even compatible with the old GVM. If you're still on GVM and you don't want to touch anything, you can still depend on a multi-platform project using the same name as before, so Apollo API, and it will continue working. A few words about Bintray and gCenter. So Bintray is a company behind gCenter, because this is where we host our artifacts, and they also have some concepts. So they don't have Gradle metadata and modules, but Bintray has the concept of repository and packages. And when we first started looking into multi-platform, we had one package per module, which means if we wanted to support more platforms, we would have to create in the Bintray UI one new package every time. And now maybe we have something like 12, or I didn't count because there are a lot of packages with all the platforms and metadata and so on. So in order to scale this, we merged all the Bintray packages into one big package, which holds multiple modules. And this is actually very convenient. It just means that we have to version all these modules together But this is fine because we release everything at once. The plugin, runtime, API, everything is released at once. To do that, we use the maven-publish plugin. So we didn't have to use any bin tray plugin or any other plugin, just the standard maven-publish plugin from Cradle allows us to publish all our modules. And the nice thing is that if you're using at the same time the multi-platform Kotlin plugin, the multi-platform plugin will create all the software components to use in maven-publish. And in the end, publication is just about making a post to some HTTP endpoint. So if you specify this, which is the bin tray API to upload your files and your credentials, then it's basically all you need to upload your files. So really, if you're a library maintainer, publish your libraries using the maven-publish. It's really easy. So a few gotchas that we learned along the way, though, is that there's a lot of moving parts. Gradle metadata is not the same as Kotlin metadata, and each of these tools have different meaning and put different concept behind sometimes the same word. So to make matter worse, there is some kind of legacy. You might have seen these dash common or dash native modules that sometimes hold a GVM. So you end up having to depend on native to pull some GVM artifacts. That feels a bit weird. But the good thing is that this is mostly legacy. And if you look at the release from Kotlin 1.4 from yesterday, the M2, they say that from now on, they will migrate to this new format. So it will be way more easier to consume multi-platform libraries. And also, it's using the maven-publish plugin. It's not that hard to publish them. So really, there's no way not to publish your multi-platform libraries. That was it for publication. Now that so everything there is available, so you can test the Apollo core, you can test the runtime. And now I will leave the room to Ivan that will talk a little bit more about code generation and what's coming in the Apollo runtime.
Yeah, thank you, Martin. So let's go back a little to our code generation. And so this is how our code generation works. So basically it takes the compiler configuration, it takes the GraphQL schema, and also obviously it takes the GraphQL query and parse it and generates some Kotlin file. So basically, if you have this kind of GraphQL query, it will generate similar to this Kotlin file, where we can see that you can compose the GraphQL request host body, or you can parse the response from the stream. Also, it generates the data classes, the models for your GraphQL query. For example, here we see that it generates the data class hero with the fields ID and name. So what did we do in order to make this Kotlin code to be worked on the Kotlin native? So this is our GraphQL query, and this is the Kotlin file that can be used on the Kotlin native platform. As you can see, it's the same as JVM. We really didn't do anything specific to make the generated Kotlin code to be work on the Kotlin native environment. And the reason why is, first of all, is because we are using the pure Kotlin language for generating our models. Obviously, of course, we migrated our API files or supporting files to Kotlin native. And the only thing that we really need to change in our code gen is to replace the JVM IO exception with the OQ IO exception. Also, we are working with the streams, and thank you to OQ, starting from 2.3 and 0, we now have the Kotlin native support, so we can parse the response from the stream. The same, we can compose the GraphQL request body to the byte stream. Also, the GraphQL response is represented by the JSON, so we need somehow to parse it. Internally, we have own JSON reader and writer. We took that from the Moshi library, and I believe that Moshi took from the Android OSP. Anyway, we updated the JSON reader and writer to the Kotlin first, migrated from Java to Kotlin, and then we made it to work on the Kotlin native. So that's pretty much it. That's all what we did. We only migrate all supporting files, but the code gen that produced the Kotlin files now stays the same. And it produced the files that can be consumed in Kotlin native. We just need to make sure that we put these generated files into proper folders, but that's a job for the Gradle, our Gradle plugin. So we were lucky with the code gen. Now, what about the runtime? Just to give you an idea what the runtime on Apollo. So first of all, it's responsible for the networking, and we are using HTTP and WebSockets. We have HTTP request response cache that we are using dscalar-u cache. We have the normalized cache that can be either in memory or it's use the SQLite. Also, we have the subscription that is based on ApolloGraphQL WC protocol over WebSocket. So we start thinking what that means to migrate the existing Apollo runtime to the Kotlin native. And this is like a key points that we are like evaluating. So first of all, the existing runtime was written or designed in Java thinking. So we are using some places we're using JVM concurrency constructs like atomic reference, atomic boolean, like thread pool executor, etc. SQLite, obviously, we need to store this inside the Android, so we are using SQLite from Android. Okay, HTTP client, we are using for that, for the transport layer subscription, also for our HTTP cache. Also, we have the third-party library that from New York Times, we took the specific model related to the memory cache. So it's from the New York Times store, the old one, not new one. And so we start assessment, like, okay, what that means, what we need to do in order to migrate the existing runtime to the Kotlin and to the Kotlin native. The first one is like design in Java, written Java, cool. We can just convert Java to Kotlin and it's okay. JVM concurrency, kind of okay. Like we could try to abstract all these atomic thread pool with the workers, etc. SQLite, we are good here because we say thanks to the Square game, like SQL Delight is working with the Kotlin native. The one showstopper for us was that first is that the OKHTTP client is not Kotlin native yet. I believe that in the future it will be supporting the Kotlin native, but for now it's not working with the Kotlin native. So this is like one big like showstopper for us. New York Times, again, is a bunch of the Java files that we need to translate to the Kotlin, but also it's deprecated now. So, but it's not like everything is like manageable. We could do that. But the problem that we realize is that we are missing the proper layers of abstraction in our existing runtime. And this is our mistake. We did a mistake when we didn't pay attention to the abstractions. And for example, by saying that we are very heavily relies on OKHTTP client and the models, and we didn't properly abstract the networking layer. So without that, it's like we can just convert the Java classes to the Kotlin, shuffle around the proper folders, and magically it's going to work on the Kotlin native environment. So after assessment, we decided that it's probably let's leave the existing JVM as is right now, and let's switch to try to write a new Apollo Kotlin, a new Apollo runtime that will be working on Kotlin that currently is under development. So when we approach it that like a new runtime, we start thinking like what is going to look like. So this is a key points of our thinking. Obviously, first of all, it will be in Kotlin, and from day one is we are going to target multi-platform projects. Now we're supporting only JVM and iOS for now. Also, the next very big decision that we made is that we are using the coroutines for our APIs as a first-class citizen and what that means is that our API is, for example, one of our API is providing a flow that emits the responses. And the reason why we think that the API is going to be more simpler, obviously it will save a lot of some stuff on our end, and it will provide the flexibility. Like, for example, if you're providing you a flow that emits a response, you can have access to all these nice operators. Like, for example, you can easily use a retry mechanism if like the GraphQL response request failed. Another, the big drawback that we, like technical debt, I would say, that we need to fix is that make sure that each feature is really pluggable. And by meaning that, so existing runtime, even if you are not using, like, for example, the cache, the HTTP cache or normalized cache, it will provide you API to get access to the normalized cache. Like, for example, you can provide the HTTP headers or fetch policies, even if you are not using the normalized cache. So we want to make each feature very pluggable and isolated from like core runtime. Obviously, we need to abstract the network transport layer because it's a platform specific, and we need to put the proper abstraction for that. And because that's a Kotlin native restricts that, and it's good because this restriction that comes with a Kotlin native, it actually leads to very to correct design of the library, more proper way of designing the application. And this also, we noticed that with the proper abstraction, we can even move the new features. Like, for example, we can serve the queries and mutation over WebSocket. With the old one, we just can only do that with the subscriptions. Or, like, for example, we can add a new feature like a query batching execution when we combine the queries into one and send as a one query. This is just a high-level, very high-level architecture overview. So we are going to have an Apollo client. This is the entry point to the new runtime. This is a user-facing, it provides user-facing APIs. Internally, we're going to have this section that's responsible for request execution. And this is going to be based on the chain of interceptors that each interceptor represents the feature. It's very similar to the OKHTTP client, how they're using the interceptor. It's the same. So just to give you example, for example, the bird token interceptor is a feature that now you can authenticate your GraphQL request. And for example, the normalized cache is going to be another interceptor that you can plug and get this feature of normalized cache. Also, we are going to obviously have the network layer, the network transport abstraction that will give us access to the networking. And by this moment, you can see that everything that is a common. It's a platform agnostic, and only implementation of the network transport is going to be platform specific. And Apollo by default provides the two implementation for the HTTP network and for WebSocket network. That will be targeting iOS and JVM. But with this abstract layer of network transport, you can actually replace the default implementation with your own implementation. For example, you can easily introduce the key-term network transport. Or another good example that for your tests, you can have your mock network transport layer. Regarding the abstraction, it's just like it's just a simple example how that looks like. For example, we have the network transport that has the API that executes requests and provides the flow that emits the GraphQL response. And we have the default implementation that on iOS is based on the NSRL session, on JVM is based on the OKHTTP client. For the WebSocket, it's the same story. We have the WebSocket factory that opens the WebSocket connection, and through the WebSocket connection, you can send data and receive via channel messages. Again, on iOS, it's based on the NSURL session. On JVM, it uses the OKHTTP client. So this is the beginning of our journey with the new Apollo runtime, but we have already something that works. So this is our new model, Apollo runtime Kotlin. This is a Kotlin native runtime. Also, that we have a sample app that is working on the iOS and using this new Apollo Kotlin native runtime. We have the master ticket that will track all the PRs that we submitting to make this new Apollo runtime. And yeah, that's pretty much it from us today. And we strongly believe that Kotlin Native has a great future. And this is our just a little small contribution to the libraries available for it. And yeah, this is ApolloGraphQL and our journey to Kotlin Native that not finished yet. And yeah, thank you so much for your time. And please feel free to reach out to us. Thanks.